Hello, we are group 14 and we will be presenting problem number 94. This problem describes a triangular prism and gives you an internal stress field by this equation right here on the bottom of your screen. So basically we're going to go through the problem and it asks us to find three things. The first one of those is a body force required for equilibrium. The second is the tractions along all of the faces. And the third one asks us to sketch the normal and tangential components on faces perpendicular to axis x3. So to start out, we can look at the body force required for equilibrium. The condition of equilibrium is that the divergence of the stress tensor plus the body force is equal to 0. The divergence of the stress tensor is given by this expression right here. And we can see that all terms of the stress tensor are 0 except for S22, which gives us a divergence of S with component 0, E1, the partial of S22 with respect to x2, and 0 for the third component. So if we look at the partial of S22 with respect to x2, we can simplify this expression to this expression to ultimately end up with rho over h times x1 minus h. So the divergence of S will give us this vector here. So revisiting the requirement for equilibrium gives us a divergence of S plus the body force is equal to the zero tensor, or the zero vector, excuse me. So we end up with this expression. We can see that B1 and B3 are 0, while B2 is negative rho over h times the quantity x1 minus h. Thus, the body force required for equilibrium is given by the component 0 in E1, negative rho over h times the quantity x1 minus h in E2, and 0 in x3.
Okay, for part B, we had to find the tractions of all the faces of the prism. And this diagram of the prism shows the faces and the vectors normal to them. So for face 1, the vector normal to that is this vector n, and for phase 2 it's negative e2, for phase 3 it's negative e1, phase 4 it's negative e, or just e3, and phase 5 is negative e3. To find the traction for phase 1, we take the stress tensor times the normal component, and we found that the normal vector has components in the E1 and E2 direction. So when we multiply the two, we find the S22 component times the E2 component of the vector n. And if we apply our boundary condition that bx2 plus hx1 minus bh1 equals 0 to our component of our stress tensor, then we find that this term drops out to equal 0, and our traction of phase 1 is 0. For phase 2, the normal vector was negative e2, and the boundary condition for this phase was that x2 equals 0. We multiply the stress tensor component of S22 by the negative 1 and find negative S2 to in the E2 component, and we go through and plug in the value for S22 and take out x2 to equal 0 from our boundary conditions, and end up with the traction of phase 2 equaling a negative rho over b times x1 minus h times x1 minus b in the E2 direction. For phase 3, 4, and 5, we found the tractions to be 0. This was because the stress tensor times the normal components, normal vectors to the face, each face, had no component in the E2 direction for either one, so all the vectors turned out to be 0. Part C, they asked us to sketch the normal and tangential components of traction on the 3 faces whose normals are orthogonal to the E3 direction, and we found those faces to be face 1, 2, and 3. And we used this equation here to find the components of the traction force, which were the normal and the shear components. And the n vector is the normal vector, and m vector is the unit vector in the plane of the surface. So for face 1, we noticed that for the normal component of the stress center was equal to 0 from our boundary conditions for face 1. So the value for our normal component was 0. This plugged in back into this equation shows that the shear also has to be 0. So both the normal and shear were 0. And for phase 2, we found from part B that the traction is equal to this expression here. And since there are no components in the E3 direction for the vector m, which is E3, which is in the E3 direction, so the shear is equal to 0, and the normal can be equated to the traction, and so we get this expression here for the normal component for phase 2. And for phase 3, we found that the traction was 0, so here we took for the normal stress, we found the dot product of negative E1 times the traction force, which was 0 for phase 3. So the normal force was also 0, and meaning that the shear would equate to 0 as well for phase 3. To summarize this, we have these graphs showing that the only component of the stress was in normal, and it was in the phase 2, and it goes from negative pi h, or negative rho h, to 0 with a quadratic shape just for the second phase.